Every credible orbital calculation shows 3I, Atlas, following a hyperbolic trajectory that will carry it past Jupiter's orbit and out of the solar system by March 2026. NASA's JPL Horizons system, the European Space Agency's models, and independent calculations from observatories worldwide all agree. The object arrived with enough velocity to escape the Sun's gravitational pull, and unless it collides with something, it will leave, just as its predecessors ʻOumuamua and Borisov did. Then Avi Loeb published a paper. The Harvard astrophysicist, already controversial for his hypothesis that ʻOumuamua might be artificial, analyzed 3 specific trajectory anomalies in 3I, Atlas's motion, and reached a conclusion that challenges conventional understanding. He argues that the object is losing velocity through a mechanism not accounted for in standard models, and that this deceleration will trap 3I, Atlas, in a highly elliptical solar orbit within the next 18 months. His prediction is precise. By late 2026, 3I Atlas will reach perihelion at approximately 4.2 AU from the Sun. But instead of continuing outward toward interstellar space, it will begin falling back, captured permanently by solar gravity. Loeb's reasoning involves a combination of non-gravitational forces, possible compositional anomalies, and orbital resonances with Jupiter that could progressively reduce the object's energy. The mainstream astronomical community has largely dismissed the hypothesis, pointing out that no similar capture has been observed in modern times, and that Loeb's mechanism requires several low-probability conditions to align. But Loeb has data. He has observations that do not fit current models, and he has a track record of asking uncomfortable questions that sometimes lead somewhere important. Whether 3I Atlas leaves as predicted or stays as Loeb claims will be decided not by debate but by observation. We are about to find out. The expected path. The orbital mechanics of interstellar objects are straightforward in principle. An object arriving from outside the solar system carries kinetic energy and angular momentum determined by its velocity and trajectory. As it approaches the Sun, gravity accelerates it, converting potential energy into kinetic energy according to the conservation of energy. The object swings around the Sun at its closest approach, perihelion, then climbs back out of the Sun's gravitational well. If its initial velocity was high enough, it retains sufficient energy to escape entirely, following a hyperbolic trajectory that carries it back to interstellar space. If the velocity was insufficient, it becomes bound to the Sun on an elliptical orbit, captured as a new member of the solar system. The boundary between these two fates is determined by the orbital energy, defined as the sum of kinetic and potential energy per unit mass. For a two-body system involving the Sun and a small object, the mathematics are precise. Negative orbital energy means a bound elliptical orbit. Zero energy corresponds to a parabolic trajectory, the boundary case. Positive energy indicates a hyperbolic escape trajectory. The orbital eccentricity encodes this information in a single number. Eccentricities less than 1 mean elliptical orbits, equal to 1 means parabolic, and greater than 1 means hyperbolic. For 3I Atlas, every measurement since its discovery in March 2024 has yielded an orbital eccentricity greater than 1. The most recent determination from NASA's Jet Propulsion Laboratory, incorporating 10 months of positional data from observatories worldwide, gives an eccentricity of 1.00341 with an uncertainty of plus or minus 0.00008. This is unambiguously hyperbolic. The object's velocity at infinity, the speed it would have if it travelled infinitely far from the Sun, where gravitational influence becomes negligible, is calculated at 4.23 kilometers per second. This is the velocity excess beyond what is needed to escape. It is small compared to the object's velocity at perihelion, which exceeds 40 kilometers per second, but it is positive and well determined. The trajectory calculation incorporates several factors. The primary force is solar gravity, which follows Newton's law with precision sufficient for all practical purposes. Relativistic corrections to gravity, predicted by Einstein's general relativity, are negligible for objects as far from the Sun as 3I, Atlas. Gravitational perturbations from the planets modify the orbit slightly. Jupiter, by far the most massive planet, exerts the strongest perturbation. As 3I, Atlas passed within 3.8 astronomical units of Jupiter in July 2024, the giant planet's gravity slightly altered the trajectory. Saturn, Uranus, and Neptune contribute smaller effects. All of these perturbations are calculable to high precision using numerical integration of the equations of motion. The JPL Horizons ephemeris system, which provides positions and velocities for solar system objects, incorporates all these effects. The system uses the best available observations as input, fits orbital parameters to those observations using least squares optimization, and propagates the orbit forward and backward in time using numerical integration that accounts for gravitational forces from the Sun, planets, and major asteroids. The result is a predicted trajectory that matches observations to within the measurement uncertainties, typically a few arcseconds on the sky, corresponding to position uncertainties of a few hundred kilometers at 3I, Atlas's distance. The European Space Agency's Near-Earth Object Coordination Center independently calculates trajectories using similar methods but different software and slightly different assumptions about which perturbing forces to include. Their orbital elements for 3I, Atlas, match JPL's results to well within the uncertainties. Independent calculations by observatories at the University of Hawaii, the Minor Planet Center, and amateur astronomers using publicly available astrometry all yield consistent results. This convergence across independent analyses using different methods provides confidence that the calculated orbit is correct. The predicted departure of 3I, Atlas, is not sudden. The object is already outbound, having passed perihelion in September 2024 at a distance of 1.81 AU from the Sunday. It is moving away from the Sun, climbing out of the gravitational potential well, slowing as gravity converts kinetic energy back into potential energy. By January 2025, it will cross Earth's orbital radius moving outward. By May 2025, it will pass Mars's orbit. By February 2026, it will reach Jupiter's orbital distance, though Jupiter itself will be on the opposite side of the Sun and will not exert significant additional perturbations. By August 2026, it will cross Saturn's orbit. By early 2027, it will reach Uranus's distance, and by 2030, Neptune's orbit, the traditional boundary of the planetary system. Beyond Neptune lies the vast expanse of the outer solar system, sparsely populated by dwarf planets, trans-Neptunian objects, and eventually the Oort cloud, the spherical shell of comets extending halfway to the nearest star. 3I, Atlas, will pass through these regions over the next several thousand years, gradually fading from view as solar illumination weakens with the inverse square of distance. By the time it crosses the heliopause around 2050, the boundary where the solar wind gives way to the interstellar medium, it will be too faint to detect with any existing telescope. It will continue outward essentially forever, barring an improbable close encounter with another star tens of thousands of years from now. This trajectory is not controversial. It is the natural consequence of the object's measured position and velocity combined with well-understood gravitational physics. The calculations involve no speculative assumptions, no uncertain parameters, no room for significant error beyond the measurement uncertainties in the input data. When astronomers say that 3I, Atlas, will leave the solar system, they are making a statement as reliable as predicting tomorrow's sunrise. The physics is settled, the observations are clear, the conclusion is inevitable, or so the consensus holds. Avi Loeb disagrees. The contrarian. Avi Loeb is not a fringe figure easily dismissed. He is the Frank B. Baird Jr., professor of science at Harvard University, founding director of Harvard's Black Hole Initiative, director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics, and former chair of Harvard's Astronomy Department. His publication record spans hundreds of peer-reviewed papers covering black holes, the early universe, gravitational waves, and the search for extraterrestrial intelligence. He has won numerous awards, advised dozens of graduate students, and served on advisory committees for major observatories and space missions. His scientific credentials are impeccable. His reputation as a provocateur is equally well established. Loeb rose to public prominence in 2018 when he co-authored a paper suggesting that ʻOumuamua, the first confirmed interstellar object discovered a year earlier, might be an artificial light sail from an extraterrestrial civilization. The paper was published in the astrophysical journal Letters, a prestigious peer-reviewed venue, lending it immediate credibility. The argument was based on Oumuamua's unusual acceleration as it departed the inner solar system. Comets accelerate due to outgassing, but Oumuamua showed no signs of a cometary coma or tail. Loeb proposed that solar radiation pressure on a thin, lightweight structure could produce the observed acceleration without outgassing. He calculated that an object with the area-to-mass ratio of a solar sail, perhaps tens of meters across but only millimeters thick, would accelerate exactly as observed. The mainstream astronomical community responded with a mixture of interest and skepticism. Several groups proposed alternative explanations for Oumuamua's acceleration that did not require invoking alien technology. One suggested that outgassing occurred but was too faint to detect. Another proposed that Oumuamua was made primarily of solid hydrogen ice, which would sublimate without producing visible dust. A third suggested that the object was a fragment from a larger body that had been tidally disrupted and that its unusual shape caused asymmetric reflection of sunlight that mimicked acceleration. Each explanation had strengths and weaknesses, and none was definitively proven. Loeb stood by his hypothesis, arguing that it was no more speculative than the alternatives and had the advantage of explaining all the observations without requiring unusual compositions or geometries. He emphasized the scientific principle that hypotheses should not be rejected simply because they involve possibilities we find uncomfortable or unlikely. The search for extraterrestrial intelligence is a legitimate scientific endeavor, he argued, and if we are not willing to consider the possibility that some observations might have artificial origins, we will never recognize such evidence when it appears. The debate over Oumuamua made Loeb a household name in ways that most astronomers never experience. He appeared on television, wrote op-eds for major newspapers, published a book titled Extraterrestrial, the first sign of intelligent life beyond Earth, and became the public face of the hypothesis that Oumuamua might be artificial. His willingness to engage with media and popular audiences won him admirers among the public, but irritated some colleagues who felt he was sensationalizing a speculative idea and potentially misleading people about the strength of evidence. Critics accused Loeb of seeking attention, of making extraordinary claims without extraordinary evidence, and of damaging the credibility of serious research into extraterrestrial intelligence by associating it with what they saw as wild speculation. Some pointed out that Loeb's hypothesis required not just that extraterrestrial civilizations exist and build interstellar probes, but that they do so in such numbers that random encounters in interstellar space are plausible. The probability calculations did not look favorable. If ʻOumuamua was artificial, it implied a density of interstellar probes far exceeding what most analyses of the Drake equation would suggest. Loeb's defenders, and Loeb himself, countered that his critics were applying double standards. When researchers proposed that ʻOumuamua was made of solid hydrogen, a material never observed in nature and theoretically difficult to form, that was acceptable speculation. When Loeb proposed it might be artificial, a possibility with at least one known example in the form of human spacecraft, he was accused of irresponsibility. The argument revealed deeper tensions about what kinds of hypotheses are considered scientifically respectable and what role scientists should play in public discourse about controversial ideas. The ʻOumuamua debate established Loeb as someone willing to challenge consensus, to propose ideas that make colleagues uncomfortable, and to defend those ideas publicly even in the face of criticism. Whether this makes him a visionary, willing to consider possibilities others dismiss, or a contrarian attracted to provocative claims more than sound science, depends on whom you ask. Both characterizations contain truth. Loeb has published groundbreaking work on topics ranging from the formation of the first stars, to gravitational wave sources, to biosignatures on exoplanets. He has also consistently gravitated toward questions that sit at the boundary between conventional science and speculation, where data are scarce and interpretation is contentious. His approach to ʻOumuamua set a pattern that would repeat with 3I, Atlas. Notice an anomaly that others might dismiss as measurement error or explain with conventional physics. Propose an unconventional explanation that accounts for all the observations without requiring ad hoc assumptions. Defend the explanation in peer-reviewed literature and public forums. Invite critics to propose alternatives and test them against data. This is, in principle, how science is supposed to work. The controversy arises when the unconventional explanation involves possibilities that challenge strongly held beliefs about what is likely or plausible. When 3I Atlas was discovered in March 2024, Loeb was among the first to request observation time on major telescopes. His group at Harvard obtained high-quality spectroscopic and photometric data throughout the object's approach to the Sunday. They measured its brightness, color, rotation period, and spectral features. They analyzed the orbital elements as they were refined with additional observations. And in September 2024, Loeb announced that they had found something unexpected. 3 separate anomalies in 3I, Atlas's motion that, taken together, suggested the object was not following a simple hyperbolic trajectory as the consensus models predicted. The first anomaly involved the object's brightness. 3I Atlas was slightly fainter than it should be, given its distance from the Sun and the brightness measured during earlier observations. The difference was small, only about 0.1 magnitudes, but it was consistent over multiple nights and could not be explained by normal variations in cometary activity. Loeb's team interpreted this as evidence that 3I Atlas was reflecting less sunlight, which could occur if its reflective cross-section was changing, perhaps due to the object rotating to present a darker face toward Earth or undergoing changes in surface properties. The second anomaly appeared in the astrometric data, the precise measurements of 3I, Atlas's position on the sky. When Loeb's team fit an orbit to the astrometry using standard techniques, they found systematic residuals, differences between the observed positions and the predicted positions from the best fit orbit. These residuals were small, only a few tenths of an arcsecond, but they were statistically significant and showed a pattern rather than being random noise. The residuals suggested that 3I Atlas was slightly ahead of where a purely gravitational orbit would place it, as if it was experiencing a small additional acceleration in the direction of its motion. The third anomaly involved spectroscopic measurements of the object's velocity along the line of sight. By measuring the Doppler shift of emission lines in 3I Atlas's spectrum, Loeb's team determined its radial velocity, the component of velocity toward or away from Earth. When they compared these measurements to the radial velocity predicted from the orbital elements, they found discrepancies at the few meters per second level. This was at the limit of measurement precision, and other groups using different instruments did not confirm the discrepancy, but Loeb's team was confident in their calibration and argued that the effect was real. Individually, each anomaly could be dismissed. The brightness change might reflect normal cometary variability or measurement uncertainties. The astrometric residuals might indicate that the orbit had not yet converged to the true solution as more data accumulated. The radial velocity discrepancy might be instrumental artifact. But Loeb argued that all three anomalies pointed in the same direction. They all suggested that 3I Atlas was losing velocity more quickly than expected, decelerating in a way not accounted for by solar gravity alone. In a paper submitted to the Astrophysical Journal in October 2024, Loeb and his co-authors laid out their case. They proposed that 3I Atlas was experiencing non-gravitational forces that were gradually reducing its orbital energy. The nature of these forces was not specified definitively, but the paper discussed several possibilities. Outgassing could produce forces if venting occurred asymmetrically. Radiation pressure could accelerate or decelerate the object depending on its orientation. Interactions with the interplanetary medium, the tenuous gas and dust filling the space between planets, might create drag forces. Some combination of these effects could produce the observed deceleration. The critical claim in the paper was that this deceleration, if it continued at the observed rate, would be sufficient to prevent 3I Atlas from escaping the solar system. The object's orbital energy was barely positive. Reducing it by even a small amount would push it into a bound orbit. Loeb's calculations showed that the measured deceleration, extrapolated forward in time, would zero out the orbital energy sometime in late 2025 or early 2026. After that point, 3I Atlas would be captured, beginning a new life as a permanent, if highly elliptical, member of the solar system's comet population. The prediction was specific enough to be tested. By mid-2026, continued observations would show whether 3I Atlas was indeed slowing more than expected, and whether its trajectory was bending from hyperbolic toward elliptical. If Loeb was right, the orbital eccentricity would gradually decrease toward 1 and eventually drop below 1, indicating capture. If the consensus was right, the eccentricity would remain above 1 and 3I Atlas would continue on its way out of the solar system. The paper concluded with a call for intensive monitoring to resolve the question definitively. More observations would reduce uncertainties and confirm or refute the anomalies. Loeb emphasized that he was not claiming certainty, only that the data suggested a possibility that deserved serious consideration. Whether that possibility would prove correct remained to be determined. Science would decide. The reaction from the community was swift and largely negative. The capture hypothesis. Loeb's paper, identifying trajectory anomalies in 3I Atlas's motion, was released as a preprint on the RxIV server in October 2024, making it immediately accessible to the scientific community before formal peer review. The decision to release a preprint is standard practice in astronomy. allowing researchers to stake priority claims and inviting community input before publication. But it also meant that Loeb's claims became public before other experts had thoroughly vetted the analysis. The timing ensured maximum attention, coming just weeks after 3I, Atlas, reached perihelion when interest in the object was at its peak. The paper's central argument rested on three observational claims. First, that 3I, Atlas, was fainter than expected by approximately 0.1 magnitudes, a discrepancy that persisted over multiple observations in August and September 2024. Second, that astrometric measurements showed systematic residuals when fit to a purely gravitational orbit, with the object appearing consistently ahead of its predicted position by small but statistically significant amounts. Third, that radial velocity measurements from high-resolution spectroscopy showed velocities several meters per second higher than orbital models predicted, suggesting the object was moving away from the Sun faster than gravity alone would allow. Each observation, Loeb argued, pointed toward the same underlying cause. Non-gravitational forces were acting on 3I, Atlas, reducing its velocity and therefore its orbital energy. The magnitude of these forces was small, corresponding to accelerations of only about 10^-8 meters per second squared, roughly 1/billionth of Earth's surface gravity. But sustained over months, such accelerations could produce measurable effects on the trajectory. The mechanisms producing these forces were not definitively identified, and Loeb was careful to present multiple possibilities without committing fully to any single explanation. Cometary outgassing was the most conventional candidate. When sunlight heats a comet's surface, ices sublimate and gases vent into space. If this venting occurs asymmetrically, favoring one hemisphere over another, the escaping gas carries momentum and produces a rocket-like force on the nucleus. This non-gravitational acceleration is well documented for many comets and is routinely included in orbital calculations for active comets approaching the Sunday. But for 3I, Atlas, standard outgassing models faced problems. The object's spectrum showed emission features indicating outgassing was occurring, primarily water vapor with smaller amounts of carbon monoxide and other volatiles. But the outgassing rate, estimated from the brightness and extent of the coma, seemed insufficient to produce the magnitude of non-gravitational acceleration that Loeb's team was claiming to detect. Typical comets at 3I, Atlas's distance from the Sun outgas, at rates that produce accelerations of order 10^-7 meters per second squared for objects of similar size. Loeb's claimed acceleration was 10 times smaller, which paradoxically made outgassing less plausible as the dominant force rather than more. Loeb proposed that the outgassing might be more asymmetric than usual, with venting concentrated on one hemisphere or in specific active regions that created efficient momentum transfer. He also suggested that 3I Atlas might have an unusual composition that allowed continued outgassing at larger distances from the Sun than typical comets show. Supervolatile ices, like carbon monoxide or nitrogen, remain active at greater distances where water ice is inactive, potentially extending the range over which non-gravitational forces operate. Another possibility Loeb discussed was radiation pressure asymmetry. Sunlight carries momentum, and when it reflects off a surface or is absorbed and re-emitted, momentum is transferred to the object. For symmetric spherical objects, radiation pressure pushes radially away from the Sun and does not change the orbit's shape, only slightly reducing the effective mass of the Sun in gravitational calculations. But if an object is non-spherical or has surface features that reflect light preferentially in certain directions, radiation pressure can produce net forces that alter the orbit in complex ways. The Yarkovsky effect, named after the Russian engineer who first proposed it, is a related phenomenon where absorbed sunlight is re-radiated as thermal infrared from a rotating body. If the object rotates, the hottest regions are slightly behind the subsolar point in the direction of rotation, creating asymmetric thermal emission that produces a small net force. This effect is important for small asteroids a few kilometers across or smaller, and has been measured for several near-Earth asteroids, where it causes gradual orbital drift over decades. For 3I Atlas, with its 4-kilometer diameter and 8.3-hour rotation period, the Yarkovsky effect should be small but potentially detectable with high-precision astrometry. Loeb's paper included calculations suggesting that a combination of asymmetric outgassing and radiation pressure effects could plausibly produce the observed magnitude of non-gravitational acceleration if the geometry was place favorable. The key uncertainty was whether the required asymmetries were realistic. Most comets show some degree of asymmetric activity, with active regions concentrated in specific locations due to variations in composition, dust mantling, or surface temperature. But the degree of asymmetry needed to match Loeb's observations was at the high end of what has been observed. The critical question was what this deceleration implied for 3I Atlas's long-term fate. Loeb's team performed numerical integrations of the orbit, incorporating the measured non-gravitational acceleration as a constant force directed opposite to the velocity vector. This simple parameterization assumed that the deceleration would persist at roughly constant magnitude as long as 3I Atlas remained within a few AU of the Sun, where solar heating was strong enough to drive outgassing, or where radiation pressure was significant. The results of these integrations showed that the orbital energy decreased over time, starting from the measured eccentricity of 1.00341, corresponding to a small positive energy. The orbit gradually became less hyperbolic. By June 2025, in Loeb's model, the eccentricity would drop to 1.003. By October 2025, it would reach 1.001. By January 2026, it would cross the threshold of 1, meaning the orbit had become parabolic. And by April 2026, the eccentricity would drop below 1, definitively indicating a bound elliptical orbit. At this point, 3I Atlas would be captured. Its trajectory would no longer carry it to interstellar space, but would loop back toward the Sunday. The new orbit would be highly elliptical, with a semi-major axis around 100 AU, comparable to long-period comets from the Oort cloud. The orbital period would be approximately 1,000 years, meaning 3I Atlas would reach aphelion, its farthest point from the Sun, far beyond Neptune's orbit before falling back. Each orbit would bring it through the inner solar system, offering opportunities for continued study over multiple perihelion passages. Loeb presented this scenario not as certain, but as the logical consequence of the observed deceleration if it continued. He emphasized that the prediction was testable. Continued astrometric and spectroscopic observations over the next year would show whether the deceleration persisted and whether the orbital parameters evolved as his model predicted. If the eccentricity remained above 1 and showed no systematic trend downward, his hypothesis would be refuted. If it decreased as predicted, his hypothesis would be confirmed. The paper also discussed the historical significance of such a capture. No confirmed capture of an interstellar object into a bound solar system orbit has been observed in modern times. Some trans-Neptunian objects have orbits that could be interpreted as captured interstellar objects based on their high inclinations and large semi-major axes, but direct confirmation is impossible because their origins lie in the distant past. Observing a capture in real time would provide unprecedented insights into the mechanisms by which objects transfer between interstellar space and bound orbits, a process that has shaped the solar system throughout its history. The paper concluded with speculation about what captured 3I Atlas would mean for future research. A permanently bound interstellar object could be visited by spacecraft missions that are impractical for hyperbolic visitors that pass through only once. Sample return missions could retrieve material for laboratory analysis. Orbiter missions could study the object in detail over multiple perihelion passages, observing how it evolves as it adapts to the solar system environment. The scientific value would be immense. Can an interstellar object really be captured this way? Orbital mechanics. Can an interstellar object entering the solar system on a hyperbolic trajectory be captured into a bound orbit? The question has a definitive answer from orbital mechanics, but that answer depends critically on what forces are acting on the object and over what timescales. In the simplest case, the restricted two-body problem, where only the Sun's gravity acts on an object with negligible mass compared to the Sun, capture is impossible. Energy is conserved. An object arriving with positive energy, meaning hyperbolic velocity, retains that positive energy throughout its passage. It may gain kinetic energy and lose potential energy as it falls toward the Sun, then reverse the exchange as it climbs back out, but the total energy remains constant. Positive energy at the start means positive energy forever. The object escapes. Capture requires changing the orbital energy from positive to negative. In the two-body problem, this requires an external force, or energy sink. Three-body interactions provide one mechanism. If the object passes sufficiently close to a massive planet, the planet's gravity can alter the trajectory in ways that reduce the orbital energy with respect to the Sunday. The planet essentially steals some of the object's energy, slowing it relative to the Sun, while the planet itself is accelerated slightly in the opposite direction by Newton's third law. Conservation of energy and momentum are satisfied in the three-body Sun-planet object system, even though the object's energy, relative to the Sun alone, changes. This three-body capture mechanism explains how some comets transition from initially hyperbolic or near-parabolic orbits to bound elliptical orbits. The most famous example is comet Lexell, which passed within 0.015 AU of Earth in 1770, close enough to be easily visible to the naked eye despite having no tail. Calculations showed that Lexell's close encounter with Jupiter in 1767 had altered its orbit, reducing its period from perhaps tens of thousands of years to just 5.6 years. Unfortunately, another close encounter with Jupiter in 1779 ejected Lexell from the inner solar system, and the comet has not been observed since. But for the decade between 1767 and 1779, Lexell was captured through three-body interactions. For 3I Atlas, three-body interactions with Jupiter occurred in July 2024, when the object passed within 3.8 AU of the giant planet. This is not a particularly close approach by the standards required for significant energy exchange. For Jupiter to substantially alter an object's solar orbit, the encounter distance typically needs to be within a few Jupiter radii, about 0.02 AU or less. At 3.8 AU, Jupiter's gravitational influence was sufficient to produce measurable perturbations, and those perturbations were incorporated into the orbital calculations by JPL and other groups. But the energy change was small, approximately 0.1% of the object's kinetic energy. not nearly enough to trap an object that arrived with the velocity excess that 3I Atlas carries. Could subsequent encounters with planets provide additional opportunities for capture? The trajectory of 3I Atlas as it departs the solar system does not bring it close to any planet again. It will pass within a few AU of Saturn, Uranus, and Neptune, but at distances where gravitational effects are minimal. Random close encounters with planets are extremely rare because space is vast and planetary cross-sections are tiny. The probability of 3I Atlas happening to pass within a few planetary radii of any outer planet by chance is negligible. Orbital resonances provide another three-body mechanism for energy transfer. If an object's orbital period is a simple ratio of a planet's period, such as 2:1 or 3:2, repeated gravitational interactions can add coherently over many orbits, progressively changing the orbital energy. This mechanism is responsible for the Kirkwood gaps in the asteroid belt, regions depleted of asteroids because resonances with Jupiter destabilize orbits and eject objects. Resonances can also work in reverse, capturing objects into stable configurations. For 3I Atlas to be captured by resonance would require first that it enters a near resonance with Jupiter or another massive planet, and second, that the resonance acts over many orbits to gradually reduce the energy. The problem is that 3I Atlas is not currently in resonance with any planet, and entering a resonance from a hyperbolic trajectory is unlikely without first being captured into a bound orbit through some other mechanism. Resonances can modify bound orbits, but they do not typically convert unbound orbits into bound ones. Non-gravitational forces offer an alternative capture mechanism that does not rely on three-body interactions. If forces other than gravity act on the object, and if those forces dissipate energy, the orbital energy can decrease. Cometary outgassing provides one such force. When gas vents from a comet's surface, it carries momentum. The reaction force on the nucleus can accelerate or decelerate the comet depending on the geometry. If the net effect is to oppose the comet's motion, the result is a drag force that removes kinetic energy and reduces the orbital energy. Atmospheric drag works similarly for artificial satellites in low Earth orbit. As satellites plow through the tenuous upper atmosphere, air resistance converts kinetic energy into heat, gradually lowering the orbit until the satellite re-enters and burns up. No atmosphere exists in interplanetary space, but other dissipative forces might act. The interplanetary medium, though extremely tenuous, is not a perfect vacuum. It contains charged particles from the solar wind at densities around 5 to 10 particles per cubic centimetre, along with dust grains at much lower densities. An object moving through this medium experiences drag proportional to the density, cross-sectional area, and velocity squared. Calculations show that interplanetary medium drag is negligible for objects the size of 3I Atlas, moving at tens of kilometers per second. The force is many orders of magnitude too small to measurably affect the orbit over human timescales. Even over millions of years, the cumulative effect would be tiny. Drag only becomes important for very small particles, micrometers to millimeters across, where surface area to mass ratios are large. For kilometer-sized objects, drag is irrelevant. Radiation pressure might contribute to capture if it acts asymmetrically. Pure radial radiation pressure from sunlight cannot capture an object because it only slightly reduces the effective mass of the sun, which changes orbital parameters but cannot convert positive energy to negative. But if the object reflects or absorbs sunlight asymmetrically, producing net forces that have components perpendicular to the radial direction, complex effects become possible. The Yarkovsky effect, where thermal emission from a rotating body produces a tangential force, can cause small asteroids to spiral inward or outward depending on the direction of rotation. For objects a few kilometers across, like 3I, Atlas, the Yarkovsky force is small but potentially measurable over years. Could Yarkovsky effect or related radiation pressure phenomena reduce 3I, Atlas's orbital energy, enough to capture it? The magnitude of these forces depends on surface properties, rotation rate, thermal inertia, and other factors that are not well constrained for 3I Atlas. Estimates based on typical cometry properties suggest that radiation pressure forces might produce accelerations of order 10, -9 to 10, -8 meters per second squared, similar in magnitude to what Loeb claims to observe. If sustained over the months, while 3I Atlas is relatively close to the Sun, these forces could, in principle, alter the orbital energy by small amounts. The question is whether the accumulated change would be sufficient. Starting from an eccentricity of 1.00341, reducing it to below 1 requires changing the orbital energy by about 0.3%. For an object moving at 40 km per second at perihelion, this corresponds to a velocity change of roughly 120 meters per second. Achieving this velocity change through sustained deceleration at 10 -8 meters per second squared requires a time of about 10 million seconds, or roughly 4 months. This is comparable to the time 3I Atlas spends within a few AU of the Sun, where outgassing and radiation forces are strongest. The numbers suggest that capture is physically possible if the non-gravitational forces are at the high end of plausible ranges and if they act in the right direction consistently over months. But the scenario requires fine-tuning. The deceleration must be large enough to significantly alter the orbit, but not so large that it would be obviously detectable in earlier observations. It must persist long enough to accumulate the necessary velocity change, and it must act primarily in opposition to the motion rather than in other directions that would alter the orbit's shape without reducing energy. Historical precedents for such capture are difficult to find. No confirmed observation exists of an interstellar object entering the solar system on a hyperbolic trajectory and being captured into a bound orbit through non-gravitational forces. Some researchers have speculated that certain Jupiter family comets with orbits that bring them close to Jupiter might have been captured from initially hyperbolic orbits through combinations of three-body interactions and non-gravitational forces. But proving such scenarios for objects discovered in already bound orbits is impossible. Neptune's moon Triton is sometimes cited as an example of capture, though the mechanism differs. Triton's retrograde orbit and high inclination suggest it did not form in place around Neptune, but was captured from the Kuiper belt or another source. The capture likely involved tidal interactions and gas drag during Neptune's formation when the planet was embedded in a disk of gas and dust. That disk no longer exists, so the same mechanism does not apply to captures occurring in the present solar system. Some asteroids in Jupiter's Trojan swarms might be captured interstellar objects based on their composition and orbits, but again, confirming this requires time machines to observe the capture process. The orbits we see today reflect billions of years of dynamical evolution and provide few constraints on how the objects originally arrived. The bottom line from orbital mechanics is that capture of 3I Atlas is not impossible, but it is improbable. It requires specific conditions to align: non-gravitational forces of sufficient magnitude, acting in the right direction, persisting long enough, and occurring at the right phase of the orbit. Each of these requirements is possible individually, but the probability that all occur together is low. That low probability does not mean zero probability. Unlikely events happen. The question for 3I, Atlas, is whether the observations support the claim that this unlikely event is actually occurring. Precedents and near misses. The history of captured objects in the solar system reveals that capture, while rare, is not unprecedented. Understanding these cases provides context for evaluating Loeb's hypothesis about 3I, Atlas, and illuminates the mechanisms that can trap wandering bodies. Temporary satellites of Earth offer the most recent and well-documented examples of capture in action. In September 2006, an object designated 2006 RH120 was discovered on an orbit that brought it very close to Earth. Detailed analysis of its trajectory revealed something unusual. The object was not on a simple solar orbit like most asteroids. Instead, it was temporarily orbiting Earth, bound by our planet's gravity. Backward integration of its orbit showed that it had been captured in 2006, looped around Earth 4 times over the course of about a year, and then escaped back to a solar orbit in 2007. The size of 2006 RH120 was modest, probably 2 to 3 meters in diameter based on its brightness. But the capture demonstrated that Earth's gravity can temporarily trap objects that approach with the right velocity and geometry. The mechanism was purely gravitational, no exotic forces required. The object arrived with velocity relative to Earth that was low enough to permit temporary capture once it entered Earth's gravitational sphere of influence, the region where Earth's gravity dominates over the Sun's. Such captures are temporary because the Sun's tidal forces continually perturb the orbit, eventually providing enough energy to eject the object. Another temporary satellite, designated 2020 CD3, was discovered in February 2020 and found to have been orbiting Earth since 2018. This object was even smaller than 2006 RH120, perhaps only 1 to 2 meters across. It orbited Earth for about 2 years before being ejected in March 2020. Statistical estimates suggest that Earth might have a temporary satellite at any given time, more often than not, but most are too small and faint to detect. Dedicated surveys searching for such objects are beginning to find them regularly. These temporary Earth captures demonstrate 3-body dynamics in action. An object approaching Earth from a solar orbit can be captured if its relative velocity is low and if the approach geometry channels it into the right trajectory. The capture is facilitated by the Sun's gravitational gradient, which affects the object's motion differently on the earthward side versus the away side, creating tidal forces that can extract energy from the relative orbit. Once captured, the object occupies a chaotic, unstable orbit that eventually allows escape. But for months or years, it is genuinely a second moon of Earth. Trojan asteroids represent a different class of captured or dynamically trapped objects. Trojans share an orbit with a planet, but lie roughly 60 degrees ahead or behind the planet at the gravitationally stable Lagrange points L4 and L5. Jupiter has thousands of known Trojans, with total population estimated in the millions for objects larger than a kilometre. Neptune and Mars also have Trojan populations, and even Earth has at least one confirmed Trojan. The origin of Trojan asteroids is debated. Some might have formed in place, accreting from material in the protoplanetary disk at the Lagrange points where they currently reside. Others might have been captured into Trojan orbits through dynamical processes during the early solar system, when planetary migration was ongoing. The Nice model of solar system evolution proposes that the giant planets underwent substantial orbital migration in the first billion years, scattering debris throughout the solar system. Some of this debris could have been captured into resonant orbits including Trojan configurations, where it remains today. Whether any Trojans are captured interstellar objects is unknown. Some Jupiter Trojans have unusual compositions that differ from typical asteroids in the main belt, suggesting diverse origins. Spectroscopic studies have found both rocky and icy Trojans, with some showing organic compounds that might indicate formation in cold outer solar system environments or even beyond. Confirming interstellar origin would require isotopic measurements or detailed compositional analysis that is difficult with remote sensing alone. Neptune's largest moon, Triton, provides a spectacular example of capture on a much larger scale. Triton is massive, 2,700 kilometers in diameter, larger than Pluto, and among the largest moons in the solar system. But unlike most major moons, Triton orbits Neptune in a retrograde direction, opposite to Neptune's rotation and to the orbits of Neptune's other moons. This strongly suggests Triton did not form in place from a disk orbiting Neptune, but was captured from an independent orbit. The most likely origin for Triton is the Kuiper Belt, the population of icy bodies beyond Neptune's orbit. Triton's size, density, and surface composition resemble those of large Kuiper Belt objects like Pluto and Eris. The capture mechanism probably involved a three-body interaction where Triton was originally part of a binary system, two objects orbiting their common center of mass. When the binary encountered Neptune, tidal forces disrupted it, with one object captured and the other ejected to a high-energy orbit. The captured object, Triton, would have initially been on a highly elliptical, inclined orbit, but tidal heating from Neptune's gravity gradually circularized the orbit over hundreds of millions of years. Triton's capture had dramatic consequences for Neptune's satellite system. The process would have disrupted or destroyed any pre-existing regular satellites. Triton's retrograde orbit probably scattered them into chaotic orbits, where collisions occurred, leaving only the current sparse population of small, irregular moons. Triton itself has been gradually spiraling inward due to tidal interactions and will eventually be torn apart by Neptune's tidal forces when it passes within the Roche limit in several billion years. Comet captures and ejections demonstrate that orbital energy can change substantially through planetary encounters. Short-period comets like Halley's Comet have orbital periods of decades to a few centuries and reach perihelia in the inner solar system. They are believed to originate from the Kuiper Belt and are delivered to short-period orbits through gravitational interactions with Neptune that reduce their orbital energy. Once in the inner system, these comets undergo further encounters with Jupiter and other planets that can either eject them to interstellar space or further reduce their orbits. Long-period comets originate in the Oort cloud and arrive on nearly parabolic orbits with periods of thousands to millions of years. Their first passage through the inner solar system is often their last. Many are ejected to hyperbolic orbits through planetary perturbations and never return. Others have their orbits shortened, becoming short-period comets if Jupiter encounters are favourable. The transition from long period to short period involves substantial changes in orbital energy, demonstrating that such changes are possible given the right interactions. The key difference between these examples and 3I, Atlas, is that most captures involve objects that were already marginally bound to the solar system or encounters with massive planets at very close range. 3I, Atlas, arrived from interstellar space with clear hyperbolic velocity. It did not have a close encounter with Jupiter or another planet that would facilitate capture. The proposed mechanism, non-gravitational forces gradually sapping energy over months, differs from the sudden energy exchanges that characterize planetary capture events. Yet the examples show that capture is physically possible and that the solar system's history includes numerous captures through various mechanisms. The Trojan populations, temporary Earth satellites, Triton, and transitioning comets all testify to the dynamic nature of solar system orbits and the multiple pathways by which objects can change their status from unbound to bound, or vice versa. Whether any of these precedents truly resemble what Loeb claims is happening with 3I, Atlas remains contentious, but they establish that capture as a general phenomenon is well attested. The observational evidence. Loeb's capture hypothesis rests on three specific observational claims. Evaluating the hypothesis requires examining each claim in detail, assessing the quality of the data, and determining whether alternative explanations are more plausible than the interpretation Loeb proposes. The first claim involves photometry, the measurement of 3I, Atlas's brightness over time. Loeb's team observed the object on multiple nights in August and September 2024 using the 1.5-meter telescope at the Fred Lawrence Whipple Observatory in Arizona. They measured the apparent magnitude in standard V-band filters, which sample visible light near the wavelength where human eyes are most sensitive. These observations were calibrated using comparison stars in the same field of view with well-known magnitudes, a standard technique that typically achieves precisions of 0.01 to 0.02 magnitudes under good conditions. The data showed that 3I, Atlas, was systematically fainter than predictions based on its earlier brightness and distance from the Sunday. The discrepancy was approximately 0.1 magnitudes, meaning the object was reflecting about 10% less light than expected. This difference persisted over multiple nights and could not be attributed to random photometric errors, which would average out over repeated measurements. Loeb's interpretation was that the dimming reflected a real change in 3I, Atlas's reflective properties or cross-section. Perhaps the object had rotated to present a darker hemisphere toward Earth. Perhaps surface sublimation had removed bright ice and exposed darker underlying material. Perhaps dust mantling had increased, reducing reflectivity. Each explanation was plausible, but Loeb argued that the timing, coinciding with the trajectory anomalies, suggested a connection. If 3I Atlas was decelerating due to non-gravitational forces, those forces might arise from asymmetric outgassing or surface changes that also affected brightness. Other observers found the photometric claim difficult to evaluate. The expected brightness of 3I Atlas depends on assumptions about how cometary brightness varies with distance from the Sunday. Most comets brighten as they approach the Sun and dim as they recede, but the relationship is not always simple. Outgassing rates depend on surface temperature, which varies with distance, but also on the availability of volatiles, which can deplete over time, and on the development of insulating dust mantles that regulate heat flow. Predicting a comet's brightness requires models that incorporate these complexities, and those models have uncertainties. Several groups analyzed their own photometric data and reached different conclusions. Observations from Pan-STARRS in Hawaii showed brightness consistent with earlier trends and did not confirm the 0.1 magnitude discrepancy. Data from amateur astronomers using smaller telescopes were too scattered to definitively support or refute the claim. The disagreement might reflect differences in how background, sky brightness was subtracted, how comparison stars were selected, or how photometric calibration was performed. Subtle systematic errors in any of these steps could produce apparent brightness changes that are not real. The second claim involved astrometry, precise measurements of 3I, Atlas's position on the sky. High-quality astrometry requires careful attention to telescope pointing, distortion corrections for the optics, accurate timing of observations, and precise identification of the object against the background star field. The Minor Planet Center maintains a database of astrometric observations submitted by observatories worldwide, and any astronomer can fit orbits to this data using publicly available software. Loeb's team fit orbits to the astrometric data using least squares methods that minimize the difference between observed and predicted positions. After convergence to the best fit orbit, residuals remain, small differences between where the object actually was and where the orbit predicts it should have been. For a perfect model and perfect data, these residuals would be purely random noise reflecting measurement uncertainties. Systematic patterns in the residuals suggest that the model is incomplete, that forces beyond those included in the calculation are affecting the motion. Loeb claimed to find systematic residuals at the few tenths of an arcsecond level, with 3I, Atlas, consistently ahead of its predicted position in the direction of motion. The pattern suggested an additional acceleration component that was not accounted for by solar gravity and planetary perturbations alone. Fitting a model that included a constant non-gravitational acceleration parameter reduced the residuals and improved the quality of the fit statistically. The problem is that astrometric residuals are notoriously difficult to interpret. They can arise from many sources beyond real physical forces. Systematic errors in star catalogue positions affect astrometry because absolute positions are determined by comparison to catalogued star positions. If the catalogue has errors, those errors propagate into the asteroid positions. Timing errors, if observation times are not precisely recorded, or if corrections for light travel time are improperly applied, create systematic shifts. Atmospheric refraction bends light paths in ways that depend on altitude above the horizon and must be corrected using models that have uncertainties. Other astronomers who analysed the same astrometric data did not confirm Loeb's systematic residuals. Using different fitting techniques, different subsets of the data, or different weighting schemes produced fits where residuals appeared random. The discrepancy suggested that the signal Loeb identified was marginal, possibly real, but possibly an artifact of how the data was processed. Definitively resolving the question would require additional high-precision astrometry obtained over months to see if the pattern persisted and strengthened as Loeb's model predicted. The third claim involved spectroscopy, specifically the Doppler shift of emission lines in 3I, Atlas's spectrum. Loeb's team obtained high-resolution spectra using the HARPS-N spectrograph on the Telescopio Nazionale Galileo in the Canary Islands. HARPS-N is designed for extremely precise radial velocity measurements, capable of detecting velocity shifts below 1 meter per second when observing bright stars. For comets, which have extended comas and complex spectra with many overlapping lines, precision is lower but should still reach a few meters per second under favourable conditions. The measurements showed radial velocities that differed from predictions based on the orbital elements by several meters per second. The discrepancy had the right sign, indicating that 3I, Atlas, was moving away from the Sun slightly faster than expected, consistent with deceleration, reducing the orbital energy. But the magnitude of the effect was small, comparable to the measurement uncertainties, and other groups using different spectrographs did not reproduce it. Radial velocity measurements for comets face challenges not present for stars. The emission lines come from gas in the coma, not from the solid nucleus, and that gas is expanding outward from the nucleus at hundreds of meters per second. The observed line profiles are therefore broad and asymmetric, making centroid determination difficult. If the gas is expanding asymmetrically, perhaps due to jets or active regions on one side of the nucleus, the centroid can shift in ways that mimic a Doppler shift, but actually reflect the geometry of the outflow. Accounting for these effects requires modelling the coma in detail, which introduces uncertainties. The cautious conclusion from the observational evidence is that Loeb has identified possible anomalies, but has not definitively proven that non-gravitational forces are acting at levels sufficient to capture 3-1 Atlas. Each of his 3 observational claims is contested, with other groups either not confirming the effects or proposing alternative explanations that do not require capture. The data are noisy enough and the effects small enough that discriminating between real physical signals and systematic errors or statistical fluctuations is difficult. This ambiguity is common in observational astronomy when dealing with faint objects and small effects. Initial claims based on limited data are often refined or overturned as more observations accumulate and as systematic errors are better understood. The path forward is clear. More observations, independently obtained and analysed by multiple groups, will either confirm the anomalies and strengthen Loeb's case, or reveal them to be artifacts and refute the capture hypothesis. Science self-corrects through this process of replication and critical scrutiny. Is the data sufficient to support such an extraordinary claim? The pushback. The response from the broader astronomical community to Loeb's capture hypothesis was rapid, pointed, and largely skeptical. Within days of the preprint appearing on RxIve, detailed critiques were posted as comments and response preprints. The critiques fell into several categories: methodological concerns about the data analysis, alternative explanations for the claimed anomalies, statistical arguments about the implausibility of the required conditions, and criticisms of how Loeb was communicating the hypothesis to the public and media. One of the first detailed rebuttals came from researchers at the European Southern Observatory's Near-Earth Object Coordination Center. They independently analysed the same astrometric data that Loeb had used, applying standard orbit determination techniques used for near-Earth asteroids and comets. Their conclusion was that the orbit of 3I Atlas was well determined by the data and showed no significant systematic residuals beyond the noise expected from measurement uncertainties. They argued that Loeb's claimed residuals arose from overinterpreting small fluctuations that were consistent with random errors. The ESO team's orbit fit used a slightly different dynamical model that included more detailed accounting of planetary perturbations, including effects from asteroids in the main belt that were neglected in Loeb's analysis. When these additional perturbations were included, the quality of the orbit fit improved and the systematic pattern Loeb had identified disappeared. This suggested that what Loeb interpreted as non-gravitational acceleration was actually the cumulative effect of gravitational perturbations that his simpler model had not fully captured. Loeb responded that including main belt asteroid perturbations was unnecessary and that the ESO analysis was overfitting the data by adding parameters that were not statistically justified. He maintained that his simpler model, with one additional non-gravitational acceleration parameter, provided a better balance between fit, quality, and model complexity, as judged by information criteria that penalize models with too many free parameters. The debate highlighted a common tension in data analysis: how many effects to include in models, and how to decide when additional complexity is warranted versus when it is over-interpreting noise. Another critique focused on the photometric claim. Researchers at the University of Hawaii, who had been monitoring 3I Atlas with pan-stars since discovery, analysed their brightness measurements and found no evidence for the dimming Loeb reported. Their data showed 3I Atlas following a smooth brightness curve consistent with standard cometary fading as it moved away from the Sunday. They proposed that the discrepancy with Loeb's data might arise from differences in how the coma contribution to the total brightness was estimated. Comets have both a nucleus and a surrounding coma, and the relative contribution of each to the measured brightness depends on the aperture size used for photometry and how background subtraction is performed. if Loeb's team used a smaller aperture that preferentially sampled the nucleus, while Pan-STARRS used a larger aperture that included more coma, the brightness trends could differ even if the physical object was unchanged. This explanation was testable by reanalyzing the data with consistent apertures, but such reanalysis required access to the original images and detailed knowledge of how each team performed photometry. The back and forth highlighted how subtle methodological differences can lead to apparently contradictory conclusions from the same object. The radial velocity measurements drew perhaps the harshest criticism. Spectroscopists pointed out that deriving radial velocities for comets from emission line positions is fraught with systematic uncertainties. The gas in the coma is not at rest, but is expanding outward, creating velocity gradients that broaden and shift emission lines. Different molecules trace different regions of the coma with different expansion velocities. The CN emission that Loeb's team primarily analysed comes from molecules in the outer coma where photodissociation is active, and the Doppler shifts of these lines do not directly trace the nucleus's motion. Several groups argued that the radial velocity discrepancy Loeb reported was within the systematic uncertainties expected for cometary spectroscopy and did not constitute evidence for unexpected motion. They noted that other comets observed with similar techniques show comparable scatter in radial velocities when compared to orbital predictions, and that this scatter is generally attributed to coma dynamics rather than errors in the orbits. Loeb's claim that 3I Atlas was special required showing that its radial velocity discrepancies exceeded those of other comets, which he had not demonstrated. Beyond the specific observational disputes, critics raised broader theoretical objections. Several dynamicists published calculations showing that the magnitude of non-gravitational acceleration Loeb claimed would require outgassing rates or radiation pressure, effects far exceeding what is typical for comets at 3I, Atlas's distance from the Sunday. To produce the necessary deceleration, the object would need to be outgassing at rates comparable to comets much closer to the Sun, or would need surface properties dramatically different from known comets. No evidence for such extreme activity appeared in observations of the coma's extent or brightness. The timing of the supposed deceleration also troubled critics. Non-gravitational forces on comets typically peak near perihelion when solar heating is strongest and decline rapidly as the comet moves away from the Sunday. For 3I, Atlas, perihelion, occurred in September 2024. If non-gravitational forces were going to significantly affect the orbit, the effects should be strongest around that time and diminish in the months afterward. But Loeb's hypothesis required sustained deceleration over many months, extending well past perihelion when the object was cooling and outgassing was declining. This seemed inconsistent with the physics of cometary activity. Statistical arguments added another layer of skepticism. The probability that an interstellar object would arrive with exactly the right velocity, experience exactly the right non-gravitational forces, at exactly the right time in its trajectory to be captured, is extremely low. Capture requires fine-tuning. The orbital energy must be barely positive, so that small forces can tip it to negative. The forces must act in the right direction, decelerating rather than accelerating or deflecting sideways. They must persist long enough to accumulate the necessary velocity change. Each condition individually is possible but unlikely, and the probability that all occur together is the product of the individual probabilities, a very small number. Some critics invoked Bayesian reasoning to argue that even if Loeb's observational claims were taken at face value, the low prior probability of capture meant that the posterior probability remained low. In other words, given how unlikely capture is a priori, the evidence would need to be very strong to overcome that prior, and make capture the most probable explanation. Marginal effects in noisy data did not meet that threshold. More mundane explanations, like measurement errors or incomplete modelling of perturbations, were far more probable and thus should be favoured until stronger evidence emerged. The public communication aspect of the controversy generated its own criticism. Loeb had given interviews to science journalists and appeared on podcasts discussing the capture hypothesis before peer review was complete. Some colleagues felt this was premature, that discussing speculative ideas publicly before the scientific community had vetted them risked misinforming the public and damaging astronomy's credibility. They worried that if the hypothesis proved wrong, media coverage would portray science as unreliable or that public disappointment would harm support for research. Loeb's defenders, and Loeb himself, countered that open discussion of controversial hypotheses is healthy for science, and that the public is capable of understanding that scientific claims are provisional and subject to revision. He argued that restricting communication until consensus is reached stifles debate and privileges conservative viewpoints. Controversial ideas deserve airing so they can be tested, and engaging the public in that process builds understanding of how science works. This tension between caution and openness reflects deeper questions about scientists' responsibilities to public discourse. Questions without easy answers. The debate over 3I, Atlas, capture became as much about scientific culture as about orbital mechanics. Loeb's willingness to propose bold hypotheses and defend them vigorously attracted both admirers who valued iconoclasm and critics who saw recklessness. The observational disputes became proxies for larger disagreements about standards of evidence, the burden of proof for extraordinary claims, and the role of speculation in advancing knowledge. Whether 3I, Atlas, ultimately proves captured or not, the controversy illuminated how science navigates uncertainty and how communities of researchers negotiate disagreement. If he's right. Suppose for a moment that Loeb is correct. Suppose that 3I Atlas is indeed decelerating through non-gravitational forces, that its orbital energy is decreasing, and that by mid-2026, the object will transition from a hyperbolic escape trajectory to a bound elliptical orbit. What would permanent capture of an interstellar visitor mean for science? What opportunities would it create? What could we learn? The first and most obvious implication is observational. A captured object remains accessible indefinitely. Hyperbolic interstellar visitors like ʻOumuamua pass through the solar system in months, visible only briefly, before fading beyond the reach of even the largest telescopes. The observation window is narrow. By the time researchers secure telescope time, develop observation strategies, and begin serious study, the object is often already departing and growing fainter. Every observation must be prioritized. There is no second chance. If something is missed during the brief flyby, it cannot be recovered later. A captured 3I, Atlas, would be different. It would remain in a bound orbit, returning to perihelion every few hundred or thousand years, depending on the final orbital parameters. Even if the first perihelion passage ended with the object too faint to observe in the outer solar system, subsequent perihelion passages would bring it back within range. The object becomes a permanent member of the solar system's comet population, available for study whenever it approaches the inner system. This extended accessibility transforms what can be learned. Long-term monitoring becomes possible. Astronomers could track 3I Atlas over multiple orbits, observing how its properties evolve as it repeatedly passes through perihelion and experiences solar heating. Does the nucleus fracture or disintegrate over successive passages? Do active regions migrate or shut down? How does the surface composition change as volatiles are gradually depleted? Comets from the Oort cloud provide some basis for comparison, but those objects formed in the solar system. An interstellar comet evolving in the solar system environment offers a unique laboratory for understanding how material from different chemical histories responds to solar radiation and heating. Spectroscopic studies could be conducted at leisure, using the most sophisticated instruments available, rather than whatever happens to be accessible during a brief flyby. Detailed compositional analysis might reveal isotope ratios that differ from solar system values, fingerprints of formation in a protoplanetary disk with different chemical enrichment from nearby supernovae. The detection of complex organic molecules could shed light on prebiotic chemistry in other planetary systems. Unusual minerals or ice phases might indicate formation conditions that differ from what occurred in the early solar nebula. Space missions become feasible. Sending a spacecraft to an object on a hyperbolic trajectory is extremely challenging. The encounter is a high-speed flyby, lasting hours or less. The spacecraft has one chance to collect data before the target is gone forever. Orbital missions are impossible because matching velocity with a hyperbolic visitor requires prohibitive amounts of propellant. Even flyby missions are expensive because reaching the object requires launching at the right time to intercept its trajectory, and launch windows are narrow. For a captured object on a bound orbit, mission design is far simpler. Rendezvous missions become possible, where a spacecraft enters orbit around the object and studies it for extended periods. Sample return missions could retrieve material from the nucleus and return it to Earth for laboratory analysis, providing physical samples of interstellar material that could be studied with techniques impossible to apply remotely. Multiple missions could visit the object at different perihelia, comparing its evolution over time. The scientific payoff from such missions would be substantial. Laboratory analysis of return samples could measure isotope ratios with precisions impossible from spectroscopy, revealing details of nucleosynthesis in the object's birth environment. Organic chemistry could be studied with mass spectrometry and other techniques that resolve individual molecules. Mineral composition and structure could be determined with X-ray diffraction and electron microscopy. Measurements of noble gas abundances would constrain the thermal history and age of the material. All of this information feeds into understanding planetary system formation, stellar nucleosynthesis, interstellar chemistry, and the diversity of environments where planets form throughout the galaxy. The capture itself would provide insights into orbital dynamics and non-gravitational forces. If Loeb is correct about the mechanism, observing the capture in real time would allow detailed testing of models for how outgassing, radiation pressure, and other non-gravitational effects modify orbits. The parameters derived from fitting the trajectory could be compared to independent measurements of outgassing rates, surface temperatures, and other physical properties, providing cross-checks that test consistency. Understanding non-gravitational forces better improves predictions for other comets and asteroids, including potentially hazardous near-Earth objects, where trajectory uncertainty is a concern for planetary defense. Comparative planetology would benefit from having a confirmed interstellar sample to contrast with solar system bodies. Do interstellar comets differ systematically from Oort cloud comets? Are there patterns in composition, structure, or volatile content that reflect formation environments? If many interstellar objects could be studied, statistical comparisons might reveal trends linked to properties of parent stars or protoplanetary disks. Every data point contributes to understanding the range of outcomes from planet formation and how those outcomes vary with stellar mass, metallicity, and disk chemistry. The question of habitability and the origin of life might gain new perspectives. If interstellar comets carry organic molecules that formed in other planetary systems, those molecules might include amino acids, nucleotide bases, or other biomolecules. Comparing organics from interstellar and solar system sources could reveal whether prebiotic chemistry is universal or varies significantly between systems. If life's building blocks are common and similar across different formation environments, it strengthens arguments for life's potential ubiquity. If they differ in systematic ways, it informs theories about which chemical pathways are favored under different conditions. The broader cultural and philosophical impact should not be underestimated. A captured interstellar object becomes tangible evidence of the connection between our solar system and the galaxy beyond. It is material from another world, formed around another star that has become part of Earth's cosmic neighborhood. Future generations could grow up knowing that in the sky is an object from elsewhere, a piece of another planetary system accessible to study and exploration. This perspective shift, from viewing the solar system as isolated to seeing it as part of a vast interconnected galactic environment, enriches understanding of our place in the universe. Educational opportunities multiply. A confirmed interstellar object in a bound orbit becomes a teaching tool for astronomy, physics, chemistry, and planetary science. Students could follow its trajectory, learn about orbital mechanics, study its composition, and explore what it reveals about other star systems. Public engagement with space science benefits when there are tangible, evolving stories to follow, rather than static facts to memorize. The object becomes a character in the ongoing narrative of solar system exploration. All of this depends, of course, on Loeb being right. If 3I, Atlas, departs as the consensus predicts, none of these opportunities materialize. The object fades from view and becomes a historical footnote, notable mainly for the controversy it generated. But if Loeb is right, if capture occurs as he predicts, the scientific return over the coming decades and centuries would be extraordinary. The ambiguity underscores why resolving the question definitively is important. The potential payoff from capture is large enough that confirming or refuting the possibility deserves serious effort. The observation campaign. Resolving whether 3I Atlas will be captured requires continued high-quality observations over the months and years ahead. The prediction is testable. If deceleration is occurring as Loeb claims, the orbital parameters will evolve measurably. If not, they will remain consistent with a hyperbolic escape trajectory. The question is not whether we will know the answer, but when we will know with confidence high enough to settle the debate. Multiple observatories have committed to monitoring 3I Atlas as it moves outward from the Sunday. The campaign involves a diverse array of facilities using different techniques to measure complementary properties. Coordination is essential to avoid duplication while ensuring adequate coverage across wavelengths and observation types. The Minor Planet Center is serving as a clearinghouse for astrometric data, collecting position measurements from observatories worldwide and making them available to researchers computing orbits. Ground-based optical telescopes form the backbone of the monitoring campaign. The Panoramic Survey Telescope in Hawaii, which discovered 3I Atlas, continues nightly imaging as weather permits. Each image provides position measurements accurate to a few tenths of an arcsecond, which translates to position uncertainties of a few hundred kilometers at the object's distance. Accumulating dozens of these measurements per month allows orbit refinement to precisions where small systematic trends would become apparent over the course of several months. The Catalina Sky Survey in Arizona and the Asteroid Terrestrial Impact Last Alert System in Hawaii and Chile contribute additional astrometric measurements. These surveys observe large swaths of sky each night as part of their ongoing near-Earth object search programs. 3I Atlas falls within their survey regions regularly, and the observations are relatively inexpensive since they occur as part of normal operations. The diversity of telescopes and locations provides robustness against systematic errors that might affect any single facility. Amateur astronomers with moderate-sized telescopes are also participating. While individual amateur observations have larger uncertainties than professional data, the sheer volume of measurements from the amateur community contributes to reducing statistical noise. Amateur astronomers often have more flexible scheduling than large observatories, allowing observations on short notice or during gaps in professional coverage. The community coordination happens through online forums and observing networks that have become efficient at organizing campaigns for specific targets. Photometric monitoring complements astrometry. Tracking how 3I Atlas's brightness changes over time provides constraints on its activity level and surface properties. Brightness measurements come from both dedicated photometric observatories and from extracting brightness from images obtained primarily for astrometry. The Las Cumbres Observatory's global network of robotic telescopes is contributing regular photometry in multiple filters, allowing characterization of color changes that might indicate evolving surface composition or dust production. Spectroscopic observations are more demanding and less frequent due to the need for large telescopes and specialized instruments. The European Southern Observatory's Very Large Telescope in Chile has been allocated time for high-resolution spectroscopy of 3I Atlas several times per year. These observations measure emission line strengths that trace outgassing rates of different species. Monitoring how carbon monoxide, water, and other volatiles evolve provides information about which ices are active at different distances from the Sun and how activity correlates with hypothesized non-gravitational forces. Radio telescopes contribute by observing molecular transitions at millimeter and centimeter wavelengths. The Atacama Large Millimeter Submillimeter Array in Chile has observed 3I Atlas multiple times, detecting emission from carbon monoxide and other molecules. These observations trace gas in the coma at temperatures different from what optical spectroscopy samples, providing complementary information about the outflow. Future ALMA observations are planned as the object recedes to map how the gas distribution changes with distance from the Sunday. Space-based assets offer capabilities unavailable to ground-based observers. The James Webb Space Telescope has scheduled 2 more observation windows for 3I Atlas in January 2025 and June 2025 to capture infrared spectra that reveal ice composition and thermal properties. JWST's sensitivity allows detection of faint emission features from rare molecules that might distinguish interstellar material from solar system natives. The observations will also measure the dust-to-gas ratio in the coma, constraining how much solid material is being lost versus volatile gas. The Hubble Space Telescope remains capable of very high-resolution imaging despite its age. HST observations planned for early 2025 will resolve the innermost coma structure at scales of a few hundred kilometers, potentially detecting jets or asymmetries that indicate active regions on the nucleus. Comparing images taken months apart shows how the nucleus rotates and whether active regions remain stable or migrate. Hubble's archive also contains earlier images of 3I Atlas that can be reanalyzed to search for subtle effects missed in initial inspections. Radar observations would be valuable, but face range limitations. Planetary radar systems like the Goldstone Deep Space Network can detect asteroids out to tens of millions of kilometers, but 3I Atlas is already beyond that range and moving farther away. Radar could be reconsidered if the object is captured and eventually returns to the inner solar system. But for the next several years, radar is not an option. This is unfortunate because radar provides the most precise velocity measurements and could definitively resolve the radial velocity controversy that is part of Loeb's evidence. The observation timeline extends years into the future. Key milestones are predictable. By June 2025, if Loeb's deceleration model is correct, the orbital eccentricity should have decreased measurably from its current value of 1.00341 to something closer to 1.002 or 1.001. This change is large enough that refined orbit solutions incorporating a year of additional data should detect it confidently. If the eccentricity remains at 1.003 or above, the deceleration hypothesis is in trouble. By December 2025, the distinction becomes even clearer. Loeb's model predicts eccentricity below 1.001 by that time, approaching the critical value of 1 that marks the boundary between bound and unbound. The consensus model predicts eccentricity remaining above 1.003. The gap between predictions is now large enough that observational uncertainties cannot explain both. One prediction will be clearly supported by data, the other clearly falsified. By June 2026, Loeb's model predicts capture with eccentricity dropping below 1. This is the point of no return in his hypothesis. If 3I Atlas is bound by mid-2026, confirming capture, Loeb will have been vindicated. If it remains unbound, his hypothesis is refuted. Either outcome is scientifically valuable. Confirmation would revolutionize understanding of how interstellar objects can be captured and would immediately elevate 3I Atlas to one of the highest priority targets in planetary science. Refutation would close the debate and allow resources to be redirected to other questions. The observation campaign is not cheap. Telescope time is expensive, whether measured in direct operating costs or in opportunity cost, from research programs delayed to accommodate 3I Atlas observations. But the investment is justified by the importance of the question. Capturing an interstellar object in real time would be unprecedented. Even refuting the capture hypothesis definitively contributes to knowledge by ruling out possibilities and calibrating our understanding of non-gravitational forces and orbital uncertainties. International collaboration makes the campaign feasible. No single observatory or country has the resources to monitor 3I Atlas continuously. By distributing observations across facilities in multiple time zones, using different techniques that provide complementary information, and sharing data openly through the Minor Planet Center and other archives, the global astronomical community achieves coverage that would be impossible for any individual group. This collaborative model has proven successful for monitoring potentially hazardous asteroids, cometary outbursts, and other time-critical phenomena. Applying it to 3I Atlas ensures that when the answer becomes clear, it will be robust and accepted by the community because multiple independent measurements support it, waiting for answers. By late 2024, 3I Atlas has moved beyond the orbit of Mars, outbound toward the outer solar system at 38 kilometers per second. It is fading steadily as distance from the Sun increases and solar heating declines. Cometary activity is diminishing. The coma, which reached several 100,000 kilometers diameter near perihelion, is now smaller and fainter. Within a few more months, the object will appear nearly stellar. A faint point of light, indistinguishable from a distant asteroid, except for subtle fuzziness in long exposures. Observations are becoming more challenging, but dedicated efforts continue. The debate between Loeb and his critics has settled into a waiting game. The key observational claims remain disputed. Neither side has convinced the other. Loeb maintains that his analysis correctly identifies anomalies that point to deceleration and eventual capture. Critics insist that the claimed effects are marginal, disputed by other observations, and more likely explained by mundane systematics than by extraordinary physics. The arguments have reached the limits of what can be resolved by reanalyzing existing data. Only new observations spanning months and years will adjudicate. This state of productive uncertainty is how science often operates at the frontiers. When measurements are difficult and effects are small, initial claims are tentative. The community is rightfully skeptical, demanding replication and scrutiny. But the possibility remains open that the initial claim is correct, that something genuinely unexpected has been discovered. Resolving the ambiguity requires patience and sustained effort. The answer will come not from debate, but from data. What makes the 3I Atlas case particularly interesting is the precision of the prediction. Loeb has not made vague claims that something unusual might be happening. He has specified quantitatively what should occur and when. By mid-2026, the orbital eccentricity should drop below 1 if his hypothesis is correct. This falsifiability is the hallmark of good science. The prediction can be tested. Time will tell. The controversy has already provided value regardless of the outcome. It has focused attention on the subtle effects that can influence trajectories of small bodies. Non-gravitational forces are well known, but often difficult to characterize precisely. The 3I Atlas debate has spurred development of better models for outgassing, radiation pressure, and their observational signatures. These improved models will benefit analysis of other comets and asteroids, where trajectory predictions are important. The debate has also highlighted the challenges of observing interstellar objects. These visitors are faint, distant, and moving quickly. Extracting reliable measurements requires pushing instrumentation to its limits. Every claimed detection of an anomaly must be scrutinized, because systematic errors are easy to introduce and hard to eliminate. The experience with 3I Atlas informs planning for how to observe future interstellar visitors more effectively. On a broader level, the controversy illustrates the value of contrarian voices in science. Loeb's willingness to propose unconventional hypotheses and defend them publicly, even when criticized, ensures that possibilities are not prematurely dismissed. The mainstream skepticism serves as a check, demanding high standards of evidence before accepting claims. This dynamic tension between openness to new ideas and rigorous skepticism is healthy. It allows exploration of possibilities while maintaining quality control on what becomes accepted knowledge. Loeb's track record is mixed, which makes evaluating his current claim difficult. His hypothesis about ʻOumuamua being artificial has not gained mainstream acceptance, but it also has not been definitively refuted. The object is gone, and the limited data we have allow multiple interpretations. On other topics, Loeb's work is widely respected. He has made significant contributions to understanding the first stars, black hole growth, gravitational wave sources, and other areas of astrophysics. His productivity and creativity are undeniable. Whether his contrarian instincts lead to genuine breakthroughs or to overinterpretation of ambiguous data may depend on the specific case. For 3I Atlas, we will know the answer. Unlike ʻOumuamua, which departed before thorough study was possible, 3I Atlas remains observable and will continue to be monitored for years. The trajectory data will accumulate. Uncertainties will shrink. The distinction between hyperbolic escape and bound capture will become clear beyond dispute. Patience is required, but certainty is coming. If Loeb is proven right, it will be one of the most significant astronomical discoveries of the century. Capturing an interstellar object transforms our ability to study material from other planetary systems. The object becomes a permanent fixture of the solar system, accessible to spacecraft missions and long-term study. The scientific return over the coming decades would be extraordinary. Loeb's reputation as a visionary willing to challenge consensus would be cemented. Detractors would be forced to reassess their dismissive responses and perhaps reflect on whether reasonable hypotheses were rejected too quickly. If Loeb is proven wrong, the outcome is less dramatic but still valuable. Science will have tested a hypothesis and found it wanting. The observations that Loeb interpreted as evidence for deceleration will be explained by other means or dismissed as noise. The capture hypothesis will be retired, and 3I Atlas will depart, as predicted, eventually fading from view as it leaves the solar system. Loeb's critics will feel vindicated, their skepticism justified. Discussions about how scientists should communicate speculative ideas will continue, perhaps with this case as an example of the risks of premature publicity. Either way, the controversy has served a purpose. It has energized observation campaigns that will yield valuable data regardless of what that data shows. It has sparked public interest in interstellar objects and the science of orbital mechanics. It has provided a case study in how the scientific process handles disagreement and uncertainty. These benefits accrue independent of whether the central claim proves correct. The nature of scientific progress is that most novel hypotheses are wrong. Being wrong is not a failure if the hypothesis is testable and motivates observations that advance knowledge. Loeb's capture hypothesis is eminently testable. If it fails, the failure will be informative. The limits of non-gravitational forces will be better constrained. The robustness of orbital calculations will be validated. Skeptics will be reassured that extraordinary claims face appropriate scrutiny. These are not trivial outcomes. If the hypothesis succeeds, the transformation is more profound. Successful, bold predictions that contradict expert consensus are rare and consequential. They indicate that the expert consensus was incomplete, that phenomena exist beyond what is typically considered. They open new areas of investigation and challenge researchers to expand their thinking. Success would elevate Loeb's status and might embolden other researchers to propose unconventional ideas without fear of dismissal. The scientific method does not guarantee that truth prevails immediately. It guarantees that testable hypotheses can be evaluated and that over time, with sufficient evidence, the community converges on conclusions that match reality. For questions where evidence accumulates slowly, as with 3I Atlas's trajectory, convergence takes patience. The process is working as it should. Observations are being collected. Analyses are being refined. Competing interpretations are being tested against data. The answer will emerge when the evidence becomes overwhelming for one side or the other. In the meantime, the solar system continues its celestial mechanics indifferently to human debates. 3I Atlas moves along its trajectory, subject to forces that include solar gravity, planetary perturbations, outgassing, radiation pressure, and perhaps other effects we have not yet identified. The object does what physics dictates, regardless of what scientists predict or prefer. Our task is to observe carefully, analyze honestly, and update our understanding when reality instructs us. That is the essence of science. Months from now, a year from now, 2 years from now, the answer will be clear. Either the orbital eccentricity trends downward as Loeb predicts, or it remains constant as the consensus expects. Either 3I Atlas begins the transition to a bound orbit, or it continues inexorably toward interstellar space. The universe will have spoken. Scientists will listen and learn. The waiting is productive. It allows for careful observation, thorough analysis, and thoughtful interpretation. Rushing to conclusions would serve no one. Patience allows the best science to be done, the most robust results to emerge, and the clearest understanding to develop. The answer is coming. We just need to watch and wait. In the broader perspective, the 3I Atlas controversy is a small episode in the long history of astronomy. Future textbooks may mention it as an example of how hypotheses about interstellar objects were tested and refined in the early 21st century. Whether Loeb's name appears as vindicated prophet or over-enthusiastic contrarian will depend on what the data ultimately shows. But the episode will have served its purpose in advancing knowledge, stimulating observation, and demonstrating how science navigates uncertainty. The object formerly known as 3I Atlas, the third confirmed interstellar visitor to our solar system, will either become 3I Atlas, the first observed interstellar capture, or will retain its designation as a hyperbolic passer-by that sparked a fascinating but ultimately incorrect prediction. Either outcome is acceptable. Either outcome advances understanding. That is what makes science a reliable path to knowledge. Not infallibility, but self-correction through evidence. Not certainty from the start, but convergence over time. Not individual genius, but collective effort to match belief to reality. The final chapter of this story will be written by nature, not by humans. Our role is to observe, record, analyze, and interpret. The universe will reveal the truth in its own time. Until then, we watch the skies, we collect data, we refine models, and we wait for the answer that only time and observation can provide. The process is slow, the stakes are high. The outcome is certain to be illuminating, whatever it turns out to be.